So glad to welcome you to today's AGU Geodesy Early Career webinar. We're very pleased that Xiaozhu Liu will be giving today's talk. I'll give you a brief introduction, and then he will give a presentation. And everyone's got the chat and questions shut down right now, but we'll open all of that up as soon as he's done speaking. So think up questions while we're working on that. All right, just letting some more people come in. So Xiaozhu is currently a researcher at the KAUST Institute in Saudi Arabia, has also been at the Institut de Physique des Globes in France and at the Institute of Geology in China, received a PhD in geophysics in 2015 from the Institute of Geology in China, with also bachelor's and master's degrees. I think one interesting thing I learned was that he hadn't had any background in geophysics before going to graduate school, so he's learned a lot and has worked in many places around the world, including, as we'll hear about today, in California and in Tibet. Also worked in New Zealand and Iceland and Saudi Arabia, studying the rheology of all of these different places. So without further ado, I'll let you get started, and we're really looking forward to your talk.
Okay, can I start?
Yes, go ahead. See if you can change your slides.
Okay. Thank Matt for introduction. I appreciate this opportunity to present my work on this platform. About my work, I benefit from guidance from Dr. Zheng Kangsen, who is my supervisor during my PhD, and Roland Bergman. Also, I benefit from strong support from Xu Wei, Jan Klinger, and Sigurd Johnson. Wait. Let's start the first part about the Landers and the Hechtman cases. We found new rheology structure for the Eastern California shear zone. About the Landers and the Hechtman cases, they are very famous in our community. Some of the studies in the early 1990s marked the birth of space geodesy in studying tectonic deformation. For example, the first use of INSA to map earthquake deformation, the first use of GPS to study the post-seismic deformation. Later, some studies gave the first discovery of some physical processes operating after big events. Also, some studies give the first try of some modeling techniques. In the beginning, many colleagues joined this game, but several years later, Jim Savage, Fred Pollitt, Andrew Fried, and Yuri Fackel took over the game, and they published papers about these two events in a way somehow like the occurrence of characteristic or quasi-characteristic earthquakes. For example, Jim Savage, every 6 years he published a paper. So, is the game over? The answer is no. During my PhD in China, I had the courage to play this game, and I started from the most simple step, which seems to be quite naive. It's about the GPS position time series. Once we get the GPS position time series, we usually use the following equation to describe the position time series. This equation includes a linear function, the blue curve, for the background deformation, and a step function for permanent cosemic offset, and also logarithmic function for post-seismic transient. So it works well in many places. So far, looks so good. The issue is that in many places, we don't have enough GPS measurement before the recent large earthquakes. In that case, we have to encounter the trade-off between the estimate of long-term post-seismic transient and the interseismic deformation. For example, look at this animation. The black curve is the observed pattern. Inside are the two proseismic transient and the interseismic deformation, as shown by the solid red and blue line. However, if we overestimate the interseismic deformation, as shown by the blue dashed line, we will underestimate the proseismic signal. Let's look at the GPS-derived velocity field for Southern California, this map. We look at the Mojave region. Before 2015, many colleagues believe that the GPS-derived velocity across the Landers and Hechtman ruptures describe the background deformation in the near, So in that case, we found that the proseismic transient would be almost complete only 6 years after the 1999 Hechtman earthquake. For example, it's flat, you see. Also, using the GPS-derived velocity field, we get very high strain rate in the epicentral area of the two events. You see here, the magnitude is comparable to that along the San Andreas Fault. Why did the previous studies got these quite weird patterns? Is it because we had not dealt well with the trade-off between the estimate of proseismic signal and the interseismic signals? For example, the dashed line, we overestimate the interseismic, but we underestimate the proseismic deformation. The key is that we need to have pre-earthquake data good enough to constrain the pre-earthquake deformation field. So we use the pre-Landers triangulation and the trilateration data to constrain the near field deformation of the Landers and Hechtman earthquake. You see these networks here. And we use the far field GPS to constrain the far field deformation. And we check the difference between the GPS-derived velocity and the model predict velocity. We found that the residuals include 2 to 3 millimeters per year right lateral shear across the Landers and Hechtman ruptures. You see here, roughly right lateral shear. Without considering such a right lateral shear in the GPS-derived velocity, we found very high peaks of max shear strain rate in the near field, as shown by the left figure. But once we consider correcting such a right lateral shear, the GPS-derived shear strain rate is much reduced and is consistent with the pre-Landers strain rate field. Yeah. Also, once we correct the GPS position time series, we found that the proseismic deformation are more active and enduring in the near field than that determined in previous studies. Look at the red and the blue. Red is the new estimate. Yeah, and we can see a very dramatic change once we consider such a correction about the GPS velocity field. Before 2015, previous studies found that the effective viscosity of the lower crust is very high, up to 10 to the power 21 Pascal seconds, and is at least 1 order of magnitude than that of the upper mantle. So this serves as a prime example of the Coulomb-Bruley model. And now we found that the near field proseismic deformation are more active and enduring than that determined in previous studies. Look at the red and the blue curves. Red is the new one. That means the physical processes operating in the lower crust are more active than thought in previous studies. And that suggest the low crust might be more ductile, or even the low crust is weaker than that determined in previous studies. So it is a time to revisit the rheology structure for this region, and perhaps it's a time to update our knowledge of the low crust rheology for this region. To do that, we used post-Landers and post-Hechtman GPS time series to constrain polar elastic rebound in the upper crust, localize upslip on the fault plane and its extension, and distributed viscoelastic relaxation in the low crust and upper mantle. Our primary goal is to get a new estimate of the viscosity of the low crust and upper mantle. Before I show our new result, let's recheck the rheology structure favored by previous studies. You see, very strong viscosity of the low crust. Now, with the new estimate of post-seismic transients, we found that the preferred viscosity of the low crust is much reduced compared to the previous estimate. It's at least 1 times smaller. And the preferred viscosity of the low crust is only 5 times that of the upper mantle. In our studies, we used Berger's rheology, in which the steady state viscosity is determined from the 18 years GPS data after the Landers earthquake. We used GPS data in the first month, first year, and all the data to constrain the transient viscosity of the Berger's rheology. We found that the transient viscosity appears to increase with time. It is only 10 to the power 17 Pascal seconds in the first month, which is an order of magnitude smaller than that determined by all the data, which spans about 18 years. So that means we need to consider to use extended Berger's rheology, which has at least 2 transient viscosity. You see this figure. Or we need to consider to use realistic power law rheology. The strain rate is a function of stress to a power n. Yeah, this one. Unfortunately, right now, the steady state power law is well known, but we don't know too much about the transient creep, for the power law. Yeah. In this regard, Professor Andrew Fried made efforts to include transient creep in his models with power law rheology. He assumed that the transient creep has similar temperature and stress dependency as the steady state creep. And his estimate of the effective viscosity in the first month of the Hechtman earthquake is about 5 multiplied 10 to the power 18 Pascal seconds, which is an order of magnitude than our estimate, which is based on Berger's rheology. So that means we need to find a better way to include the transient creep in our models with power law rheology when we want to model the post-seismic deformation. So here are the take-home messages. First, we found post-seismic transient in the form of 2 to 3 millimeters per year in the published GPS-derived velocities. And our results are quite different from the result from many groups. And such a geometric difference occurs because many previous studies had not dealt well with the trade-off between the estimate of interseismic velocity and the long-term post-seismic transient. And the issues that is related to the such a trade-off have broader impact on GPS geodesy. For example, when we use post-earthquake GPS measurement in tectonically active regions to study the earthquake deformation, reference frame realization, and seismic hazard analysis. Sometimes we probably are using the not inaccurate GPS velocity and the GPS time series for post-seismic deformation studies, and the reference frame realization. And the second take-home message is that we found that the steady-state lower class viscosity is only 2 multiplied 10 to the power 20 Pascal seconds, only 5 times that of the upper mental, rather than greater or equal to 10, as favored by previous studies. We also found that realistic power law rheology is required to explain post-seismic GPS measurements. Okay, we finished the first part. So let's move from the low elevation Mojave to high elevation Tibet Plateau. This is my work in the last more than 2 years. So let's first look at this figure showing the topography and the distribution of active faults on the 5 kilometers high Tibet Plateau. We can see a series of north-south trending active normal faults, the purple line you see here, and the conjugate strike slip faults on the Tibet Plateau, which suggests east-west extension has been operating for some time. And such an east-west extension has been observed by GPS. For example, the blue vectors, you see expansion, somehow expansion, and the strand dilation rate derived from GPS derived the velocity field. So that means cluster extension and the thinning continues in the 5 kilometers high central Tibet, and the central Tibet should be subsiding. Now let's look at topography along this profile as marked by the black line from southwest to northeast are Himalayas, central Tibet, northern Tibet, and the stress state in the crust approximately follow the blue vectors. You see the substance in the central Tibet. But in the late Oligocene, the topography of the Tibet Plateau probably follow the red dashed line you see here. That means the northern Tibet had experienced substantial surface uplift since the late Oligocene. And now its elevation is approximately similar to that in the central Tibet, you see here. So our question is whether the ongoing substance in the central Tibet applies to the northern Tibet, because they have, you see, they have the similar elevation. Let's look at what GPS can tell us about this story. Since 2007, we have established a continuous GPS profile across the East Quantum Mountain, which is the northern edge of the northern Tibet. You see this topography. And here the blue curves, blue vectors are the GPS-derived velocity for the horizontal component. And now let's look at the profile perpendicular to the mountain range. You see the right one, we see the shortening rate is only about 1 millimeter per year from the tied up the basin to the plateau. However, the vertical rate shows 1 to 2 millimeters per year on the eastern Quinlan Mountain relative to the 2 kilometers lower Taida Basin, and such a geometric transition occurs within only 50 kilometers. And in this case, the 1 to 2 millimeters per year vertical motion cannot be compensated by the 1 millimeter per year shortening, because in this region, the regional tectonics is dominated by active strike slip faulting along the eastern Quinlan Fault, and there is no strong evidence of recent active of thrust faults in this region. So to understand such a discrepancy in the shortening and the vertical deformation, we need to understand the GPS data. We need to understand how tectonic and geodynamic processes and the climate-related surface processes contribute to our GPS-derived signals. Here, tectonics is related to the activity of faults. Geodynamic is about the internal physical processes that arise due to the stress and the physical property heterogeneity in the crust and the lithosphere. And the climate-related surface processes are the glacial activity on the summit, erosion along the hill slope and in the valleys, sedimentation in the basin, and some groundwater activity. Yeah. Because our GPS stations are located to the eastern tip of the 2001 Kokoshiri earthquake. And the observations start about 6 to 7 years after the event. So we must consider the impact from the post-seismic deformation following the 2001 event. So we use the GPS observations, both horizontal and vertical component, to constrain the post-seismic deformation models. And our preferred model gives very subtle substance to the south and very subtle uplift to the north of the 2001 rupture. And further away, we see the also very small substance and the uplift. Once we plot this along this profile, we found that post-seismic deformation cannot explain the GPS-derived vertical motion. Also, we consider how the isostatic adjustment driven by the climate-related surface processes contribute to the GPS-derived vertical motion. The idea is very simple. Look at this animation here. Once we have a mass load, there will be a subsidence where the load is located, and a very subtle uplift in the neighboring, in the adjacent regions. Yeah, here, subsidence uplift. And once it's mass reloading, unloading, we will uplift and subsidence. Let's look at 2 examples. One is about the glaciation since the Little Ice Age. The Little Ice Age started in the about 13th to 14th century until the end of 19th century. And in our case, the glacial melting after the end of Little Ice Age is about half of the ice accumulation during the Little Ice Age. And also the glacial retreat rate in the last 10 years follows the estimate based on other studies. Yeah. And we then calculate the unloading uplift caused by the deglaciation. we found a very subtle uplift localized about the modern glaciers. You see this, yeah, it's very small. And once we plot on this profile, we found it's a very small fraction of the GPS derived uplift, maybe 10%. And here, if we want to let the model to fit the GPS observed vertical motion, we need either 100 kilometers thick ice thinning after the end of little ice age, or very low viscosity of the lower crust, which is of the order of, oh, sorry, I made a mistake, 10 to the 18 pascal second. Both are unrealistic for this region. Also, I calculated the fluvial erosion for this region. And you see the erosion mostly about 0.5 millimeter per year on the high mountains, along the high mountains. And then I calculate the unloading uplift. It's also very small, and it's localized along the mountains. You see the Eastern Quinlan Mountain, the Chilean mountain like this, yeah. And once I plot on this profile, it's also very small. You see, it cannot explain the GPS-derived vertical motion. And I want to emphasize that if I want to use this model to explain the GPS observed uplift, the erosion rate must be around 10 millimeters per year. And for that's impossible for this region because it's very arid, very dry. Yeah, very dry in the last maybe 10,000 years. Yeah, since the last 10,000 years. In fact, I also consider other contributions. For example, the present-day hydrological loading, the present-day glacial activity, and also the late Pleistocene degradation, sedimentation. And once I sum all the contributions from those processes, I found that the surface processes cannot explain the GPS observed 1 to 2 millimeter per year vertical motion on the Eastern Quinlan Mountain. So that means the GPS-derived signal are many of tectonic and geodynamic origin. So here in this figure, I show the comparison between the observed and the correct GPS-derived vertical rate. You see the purple dots. So we need to understand which processes can really explain the GPS-derived uplift. The option include the first one, active thrusting along the range front fault. The second option is low crust thickening, because you see here the weak material might extrude from the central Tibet across the Eastern Quinlan Mountain and beneath the Eastern Quinlan Mountain. Yeah. And the third option is thermal erosion, because here we see the lower shear wave velocity beneath the mohole, and also the asthenospheric upwelling. About the active thrusting, if we want to use this sort of model to explain data, we found that the slip rate must be greater than 1 millimeter per year. And in this region, both geomorphological studies and seismic studies had not found the evidence for such for the presence of such thrust faults in this region. Now, about the thermal processes in the mantle, I found that these processes induce long wavelength uplift across Eastern Quinlan Mountain. Look at the long dashed line marked by 3 in the upper left figure, and the dotted line marked by 4 long wavelengths, which is inconsistent with the GPS-derived sharp gradient across the Eastern Quinlan Mountain. Yeah. So in fact, my preferred mechanism is low crust thickening, but right now my preliminary results show that it seems to be okay, but I need to revise. But yeah. But here I cannot rule out the possibility of very, very low active thrust 14 in this in the range front. So let's understand our results in the context of the entire Tibet Plateau. As I emphasized earlier, in the southernmost margin is the Himalayas. We have the active thrusting. And in the central Tibet, we have the active normal faults, crust extension, thinning, and subsidence. But in the northern Tibet, we have large strike slip faults. And some previous studies propose that the entire Tibet plateau surface, which is 5 kilometers high, should be subsiding. Look like this. Yeah, subsidence, even the northern Tibet. But now our studies found that the northern Tibet should be still glowing upward. The difference lies in here. Also, if we compare, look at the map view of our results, as well as some previous studies, we found that the margins of the Tibet plateau is still glowing upward. For example, the southeastern side, the Loman-san region here, this, and the northern edge, the eastern Queen Mountain here. This is our result. The southern part, which is the Himalayas, sure, it's uplift, it's rising. Yeah. So here is the take-home messages. We found the active uplift of about 200 kilometers wavelengths across the eastern Queen Mountain. And here the present-day tectonics is dominated by strike slip 14. And after considering all the impact from surface processes, we found the eastern Queen Mountain continue to rise at about 1 millimeter per year. Yeah, here's the uncertainty. Yeah. And low crust thickening likely drives the ongoing uplift. So finish the second one. The third part. Let's move towards New Zealand. The plate boundary between the Australia plate and the Pacific plate. The tectonic of New Zealand is closely related to two subduction zones of the opposite polarity. You see here, the northwest and southwest. Yeah. In between the two subduction zones is the Alpine fault, which was almost a pure strike slip fault about 20 million years ago. But after about 6 million years ago, as the euler pole of the plate motion shift southwestward, the plate boundary became an oblique convergent boundary. So let's look at this figure. Here's the plate motion. That means the Alpine fault is a strike slip fault with compression. And to the southeast of the Alpine fault is the Southern Alps. And generally speaking, it is an uplift on a ramp that had led to the formation of Southern Alps. Look at this figure, the right one. And the Southern Alps continues to rise as demonstrated by GPS. For example, look at this figure. In the central Southern Alps, we see about 5 millimeters per year uplift relative to the plain, low elevation plain regions. So let's look at the profile of the GPS velocity and the topography. You see, the GPS derived vertical motion correlate well with the spatial variation of the topography. So is the story so simple? The answer is no. Once we put the short-term and long-term data across the same profile, we found a lot of inconsistencies among the data. For example, let's look at the first figure. We add the erosion rate, modern erosion rate, as shown by the purple line. We see a bell-shaped pattern with the center shift towards the northwest of the main divide. And but the GPS and the long-term topography shows a symmetric pattern with a wider spatial wavelength. Next, we add the exhumation rate within 2 million years ago and 5 million years ago, as shown by the green line, green dots, and the brown curve. We can see that the short-term GPS, this dot, the long-term topography, the gray line, and the exhumation in the 5 million within the last 5 million years, the brown line has similar spatial pattern, very similar spatial pattern. But the the exhumation during the quaternary and the erosion, modern erosion doesn't. So to understand such inconsistencies in the short-term and the long-term data, we must understand, remember that the Alpine fault and the Southern Alps system is not stagnant, but is active evolving. For example, the most important feature is that the Alpine fault slips at 30 millimeters per year in the last for a few million years. Yeah, and also the plate convergence had varied over time since the last 6 million years ago. You see the Euler pose of the relative plate motion. And also along the strike of the Alpine fault, the plate convergence also changed a little bit. And also the Alpine fault system has a long strike variation of the dip. You see in the central part, it looks like shallowly dipping, but in the northeast and southwest, it's much steeper. So for example, the southeastern part of our GPS profile is was located about 80 kilometers further northeastward about 3 million years ago. And at that time, the plate convergence was quite different. I cannot say quite. It was different from the convergence at the current position. And also, in fact, the surface processes also varied a lot during this time period. Yeah, you see, right now, yeah. So that means once we get this so many short-term and long-term data, and when we see some similar patterns in the short-term and the long-term data, we cannot compare the short-term data directly with the long-term data. For example, the short-term GPS cannot be used to approximate the long-term exhumation in average during the last 5 million years. Even though many studies believe that this mountain range might be currently in equilibrium. So let's focus on the short-term GPS, which is sensitive to the perturbation from surface processes. And in this region, the erosion rate is very intense, up to 10 millimeters per year to the northwest of the main divide. And the erosion rate here is almost the fastest on our Earth. So I calculate the unloading uplift caused by erosion here. I found that the unloading uplift can be even up to almost 3 millimeters per year on the in the Southern Alps. But the relative uplift just across the mountain range is only 1 to 2 millimeters per year, or even less. That depends on the use of elastic shear thickness. Yeah, and the wavelength of the unloading uplift, look at the bottom figure, is much wider than the GPS derived uplift. And also the magnitude are quite different. So that means the GPS-derived uplift is also many of tectonic origin. So we use first we use a simple ramp and flat model to model the GPS-derived vertical rate and GPS-derived horizontal shortening. Yeah, here in the first figure A, we found the you see the model prediction follows the red and the blue curves, and the second figure is about the shortening rate. The red curve is the model predictions, and in our modeling test, because we collect the contribution from surface processes, we found that the reverse slip on the ramp is only 6 millimeters per year, which is about 3 millimeters per year lower than that on the flat decollement. Also in our case, in the next step, I also need to consider the impact from the along strike variation of the dip of alpine fault. And the reverse slip on a gently dipping ramp might explain part of the uplift about 30 to 50 kilometers southeast of the alpine fault. And this is another option to to discuss with about the presence of a backthrust fault in this region. So here is the take-home message. We found that GPS-derived uplift is mainly caused by reverse slip on a ramp decollement system, with the ramp showing a long strike variation of dip. Erosion caused only about 1 to 2 millimeters per year unloading uplift across the central southern Alps, and about 6 millimeters per year reverse slip on the ramp, dipping 46 degrees southeastward, and which is only 2 to 3 millimeters per year less than that on the flat decollement. And I want to emphasize that here the short-term GPS observed uplift cannot be used to trace the long-term exhumation. So thank you very much. I finished the talk.
Great, thanks so much. I'm gonna open up the chat and allow people to ask questions if they want to. Does anyone want to ask a question in the chat or just unmute themselves now to start us off? See lots of people clapping here, so hopefully you can tell people appreciate it. I think Roland has got a question. Go ahead, Roland, see if you can unmute yourself.
Yeah, sure. That was great. All three parts. In the Tibet case, where you have the uplift and you think you can explain it with the lower crustal flow. So if I understand correctly, to produce the uplift near the mountains, we should see subsidence further south in the central Tibet. Do we actually have good GPS data that show?
Close the margin here or no? Here. Do you mean
further
here?
South.
Like, further south.
Yeah.
Oh,
right.
here.
Here. Lower crustal flow.
Oh,
the
yeah.
flow has to come from somewhere.
Right now in that region, we don't have enough continuous GPS. At least the published one. Yeah, published one. No. Only I checked. No, only maybe 1 to 2. No. Yeah.
But you would predict that there should be subsidence to kind of feed the uplift near the mountains. Yes.
Yeah. You are talking about here. Yeah.
Okay. Thank you so much. That's great.
Great. All right, go ahead, Bill. Bill Hammond has a question for you.
Hey, thanks very much for that great talk. For the New Zealand case, maybe you mentioned this, but I didn't hear. Have there been any recent thrust earthquakes on the Alpine fault that could drive some post-seismic vertical motion?
Recent. Oh, wait. Just for the Alpine fault, this fault is in the latest stage of the earthquake cycle. which is about maybe that remember it's 300 years, roughly like this. Yeah, but and to the southwest part here, do you see the subduction here? Subduction zone here. That remember it's in 2009 we have maybe thrust event, I guess. Here you see the southwest. You see the subduction here. Here. That remember, yeah. But it's maybe it's a few. It's maybe 400 kilometers from our GPS profile. I guess, yeah, 400 kilometers away.
Okay.
Thrust event, yeah. Maybe it's thrust event. Yeah, it's in the sea. Yeah, it's 2009. Yeah.
Mhm.
Great. All right. Well, thanks, Bill. Anyone else have a question at the moment that?
Can I ask a quick question?
Yes, please go ahead.
Hey, Xiaozhou, good talk. For the Tibet part, following Roland's question, what's the mechanism of the lower crust thickening? Can you quickly explain that? Is that because of the proposed channel flow model or other mechanism?
The direct answer is quite simple because you see the lower crust material, how to say, not this. I will use another figure. Maybe topography is better. Yeah, like this. Wait, like this figure. You see, the substance in the central Tibet is very active. That makes the lower crust material moves toward the margins. But here, in the margins, we have the very strong basin here. You can look at the cursor. Taida basin, it's very strong. So it stops the movement of the low crust material.
So it's the injection of material, right? It's from the substance
from
in
the
central.
center. Yeah, from the center.
Gotcha.
Yeah.
Thank you.
Great. Anyone else have a question they'd like to pop up with? I did have a question for you, if I can ask one, based on following up on Roland's question, which is, it seems like you're making a very strong case in, I think, your talk for the need for very long time series GPS records to really be able to see these sorts of signals. And I guess my question to you is really, based on these modelings or thinking about them, I mean, can you start to make some sort of priority list of where the observations are missing, like the data is missing? Like you just said that there was some maybe non-public data that might help constrain some of these models in some areas. I'm just wondering if, there is a priority list that you could think about in terms of, okay, well, what is the unpublished data we could go after, or where are the places that have no records like this that we should start collecting data now so that maybe decades from now we can use it?
What are you talking about the vertical deformation or post-seismic deformation? Which part?
Well, I think in particular the post-seismic story, but I mean, clearly the vertical deformation is part, it's sort of related, as you made the nice case here in Tibet.
About the post-seismic deformation priority. Right now I just know, for example, even in South America, where the big events frequently occurred. In fact, we don't have enough pre-earthquake data of the recent large events because GPS just started in the maybe early 1990s, but maybe in the 1970s, 1960s, yeah, like that. We had, or even earlier in the 19th century, yeah, we still have the very big events, and the post-seismic transit might last until now, yeah, I guess. So in those regions, yeah, sure.
Great. Anyone else have a final question? All right. I don't see anyone, so I guess why don't we all thank our speaker again for a very interesting talk, and we really appreciate it. And
thank you for your giving me this chance. Yeah.
thanks so much for doing it, and look forward to our talks that's coming up next month from Stacy La Rochelle. So otherwise, we will see you all later.